join the workshop. And the morning speaker is Mezei, and he will talk about random matrix theory for the black hole interior. Please.
Thank you very much for the invitation to this workshop, and thank you all for coming. I would like to encourage everybody to ask questions during the talk. It seems that this is a manageable audience size, so let's make this into a lively discussion. So I'm going to talk about the paper that appeared in July with my excellent collaborators, Luca Iliasiu and Gabor Sárosi, and it concerns the volume of the black hole interior. In particular, we will develop a random matrix theory understanding of some aspects of the black hole interior. So as a motivation, part one of my talk will be putting the problem into context. So I will be talking about black holes and quantum chaos. And these developments are happening in an even broader new frontier where physicists are analyzing quantum dynamics in the high entanglement regime. And the motivation to do so is threefold. Currently there's exquisite experimental control over coherent isolated quantum dynamics, for example, in the setup of quantum simulators. In quantum computation, entanglement is a resource. And so if you want to do powerful computation, we'll have to understand the regime of high entanglement. And for this talk, the most relevant development is that there are new theoretical tools, in particular, new solvable chaotic models in which we can understand some of these questions. And so one cartoon of what's going on is the following. So the great successes of 20th century physics have happened in a small corner of the Hilbert space of possible states in many-body systems or in quantum field theories, namely systems, namely in states with low entanglement or low complexity. And in this corner of this small corner of the Hilbert space, the notions of universality in phase transitions and the framework of effective field theory applies. But generically, starting from an initial state in this corner, time evolution leads out from this corner into the wild, into this large zoo of complicated states in the Hilbert space. And so ADS-CFT provides a remarkable new tool, a new framework in which to talk about these questions. It geometrizes real-time quantum dynamics. And while in the, let's say, the first decade of ADS-CFT, we concentrated on the dual of this corner, namely fluctuations around empty ADS, and the dictionary is most well developed there. In recent years, the focus has shifted towards understanding holography in generic states, and generic states in gravitational theory are black hole microstates. So more concretely, the dual of this picture is provided by the following setup. So here I represented ADS space as a soup can. So the orange part is the conformal boundary of ADS, and this is where the quantum field strongly coupled quantum field theory of interest lives. And at time equal to 0, we prepare some sparsely entangled initial state, here represented by some matter distribution close to the boundary of ADS. And then this matter falls in towards the center and forms a black hole. And so this is the geometric representation of this time evolution in the quantum system. And so as you can see, here we go from some initial state that can be represented as some perturbation of ADS to a state which is a black hole microstate. Okay. So in general, in ADS-CFT, it's a fruitful enterprise to search for ubiquitous geometric features in gravity and try to understand what they represent in quantum field theory. And so in this setup, we have a fruitful crosstalk between black hole geometry and quantum chaotic dynamics. And so the picture that we had up there was of black hole formation from generic initial conditions. And this has been understood to correspond to settling to thermal equilibrium, thermalization in the dual quantum system. And so from here on, I will represent this process with a Penrose diagram. So this is just a version of this picture in 2 dimensions. So this is the asymptotic boundary, the enfolding matter distribution, the origin of polar coordinates, the singularity, and the horizon of the black hole. Okay, so once this connection was established, we can start asking more detailed questions. For example, it was understood that the fluctuations of horizons on long wavelengths and large times is universal, and there's a simplified holographic dictionary mapping this to hydrodynamics, the fluid gravity correspondence. Okay, I will skip this. And another way to connect this setup to geometry, so this setup in quantum chaotic dynamics, is that we've been talking about entanglement entropy, the entanglement contained in these states. And famously, this is computed again from geometry through an extremal surface area. So the connection is that so this is the boundary spacetime. We take a subregion A in this many dimensions, that would be an interval. And then we compute an extremal surface area anchored on the endpoints of this interval. This is the famous RT or HRT formula. And so this direction that I drew with blue represents the extra dimension in holography. Okay, so these are nice connections between geometry and quantum chaos. The question that we will be focusing on during this talk is the connection between, or the question, what is so in gravitational theories, it's a fundamental observation that the interior of black holes grow. And what do I mean by that? I anchor a codimension 1 slice, so like a time slice at time t on the boundary, so at these points, and then I simply draw a maximal volume slice through the space-time. It looks like this on the Penrose diagram. Penrose diagrams are not great at capturing distances, but if you compute the volume element on the surfaces, it turns out that the volume of these maximal volume slices is dominated by this near horizon region behavior of them. And they turn out to grow linearly in time as I move these end points or end times upwards. And so this is what I mean by the interior growing in time. And this is true both in ADS, in flat spacetime. And we will be asking, okay, we have a nice geometric object in the bulk. Can we understand or find a boundary dual of this? Or in other words, what does the growing black hole interior represent in quantum chaos? And we hope that besides learning about quantum field theory, this could help answering puzzles or questions in black hole quantum physics and perhaps even cosmology. Sometimes people relate the growing interior of black holes to the expanding space-time in cosmology. Is there any question about this introduction? Okay, if not, let's move on to the discussion of the main part of the talk, which will be an interplay between random matrix theory, which historically is well known to be connected to chaos, and the black hole interior, which is of course geometry. Okay, so here I can give you the outline now. We will discuss two candidates for this boundary dual of the growing volume. Then I will be talking about the model in which we try to answer this question, which will be Jekyll-Teitelbaum gravity. And there was a nice talk already in the workshop about JTT Gravity. So I hope I'll benefit from that introduction. And then in particular, we will provide a random matrix description of JTT Gravity. And the next step will be to understand how to represent the volume in this random matrix theory, the volume of the black hole interior. Once we set up the calculation, we will have to evaluate this quantity. And I will end with a summary. So I will now discuss two candidate quantities that have the potential of capturing this growing volume. So the first will be, not surprisingly, will be entanglement entropy. So let's see what it does. So I'm imagining that the field theory lives on a sphere of radius L, and I take my subregion of interest to be an order 1 fraction of this sphere. Okay, so the volume, as I said, after some initial transient, grows linearly in time forever from this classical GR calculation. Let's see what entanglement entropy does. We have to compute the area of extremal surface. It starts promising after initial transient, it grows linearly, but then at time of order L, I remind you that that's the linear size of the region, it saturates to a constant value. And so while entanglement entropy tracks the volume closely at early times, it saturates too early. We don't expect that there's any new gravitational phenomenon happening at this time scale. And so we conclude that this is not a good enough candidate to capture the volume growth for long times. And I would like to note that ordinary correlation functions show the same behavior. Even if we take them at very large separation, they will saturate at this time scale. And so maybe this is the right time to talk about the time scales in this out of equilibrium setup. So a very early time scale is when these transients happen, is of order beta, the inverse temperature, and this is when one-point functions settle to thermal equilibrium. Or in other words, this is when hydrodynamics starts to apply as an effective description of one-point functions. Then we touched upon this other time scale, L, the light crossing time of our system. And this is when entanglement entropy or correlation functions saturate. In recent years, it's been understood that if we consider more complicated or more subtle quantities to probe dynamics, we can actually go and understand dynamics at longer time scales. A famous example is the scrambling time, which scales with the logarithm of the entropy of the black hole that we are considering, or in holographic systems, it goes with log of n, whereas these earlier time scales were scaling with n to the 0. And so this time scale cannot be probed by conventional observables, but so-called out of time ordered correlation functions are sensitive to them. And we've learned a lot both about quantum chaos and black holes from probing them with this subtle quantity. Then the next time scale that we can consider is the entropy time, which goes with n or n to some power, depending on what particular holographic system we are considering. I won't have time to talk about this time scale, but another time scale, e to the s, has been known since the early days of quantum mechanics. It's named after Heisenberg. It's the Heisenberg time. And this is the time scale at which the time evolution basically should stop. And the intuition behind it is that any out of equilibrium initial state can be expanded in energy eigenstates, and then the evolution is simply encoded in the change of phase of these coefficients. And so any phase difference that we will encounter has this form e to the I and some energy difference multiplied by time. So energy difference is conjugate to time. And since in chaotic systems, the separation of energy levels goes as e to the minus s. If we multiply this energy separation by a time which is order e to the s, we get a random phase. So what this is supposed to capture is that by this time the state has become completely random, apart from the constraints of energy conservation. And so if we have any reasonable observable, then those also should stop evolving, because they are just linear functions of the wave function. Sorry, they are linear operators whose expectation value we are computing. And so if the state has become random, then the quantity should stop evolving. And so this time scale will be in the focus of this talk. So the second candidate was proposed by Susskind and then Susskind and collaborators to be so-called computational complexity or circuit complexity of the evolving wave function. This is a quantity that is quite unfamiliar for those of us who study quantum field theory. So let me just give a very quick intuition. And this in the setup where we have a finite dimensional Hilbert space, for example, a spin chain, and we are handed this evolving wave function, and we are also in possession of a universal quantum computer with some prescribed gate set. Then this complexity is defined to be the minimal number of gates that we need to use in our quantum computer to reproduce this state psi, starting from a reference state and with some error epsilon. Okay, so this is an extremely hard quantity to compute, but there's still some expectation of how it evolves. At early times, the expectation is that the best thing that you can do with your quantum computer to simulate this is to simulate this time evolution. So with your quantum computer, you build an infinitesimal time evolution step, and then you repeat this infinitesimal time evolution t over delta t times. You build many layers. And so the number of gates that you have to use is linear in time. So this is at early times. At late times, we discussed that the state becomes completely random. So there might be shortcuts in preparing this state with a quantum computer. In particular, by this time, if you have a finite dimensional Hilbert space, you are basically, with these time evolved states, you are spanning the whole Hilbert space. And so it's reasonable that complexity also should stop evolving. And so based on these rough arguments, Saskinen and collaborators argued that the complexity evolution in chaotic systems should look like as in this orange curve, so that it would grow linearly in time until the Heisenberg time e to the s, and then it should stop growing with some order 1 fluctuation. So it grows to exponential in the entropy and has order 1 fluctuations. And so the starting point of our work was to ask, okay, can we find new quantum gravitational effects in the growth of the volume of the interior that will stop its growth and that will make it look like more like complexity? Okay.
Wait, so what's the time scale for evaporation? Hawking time?
Oh,
black hole
that's a very good question.
We don't need to care about linear growth.
Yeah. So the reason, so it's simpler to study large black holes in ADS for exactly this reason, that they don't evaporate. Mm-hmm. And so if in flat space black holes, you are completely correct that one would have to examine whether they evaporate earlier than this time scale, and then it wouldn't matter. So I will be studying ADS black holes in this talk.
All right,
thank you for the question. Okay, so to study this question, we will have to find the simplest possible model where we can try to look for an effect. And so in search of the simplest model, we will first try to get rid of matter fields in the bot. Pure gravity is simpler than this messy collapse process. And fortunately, Hartmann and Maldacena taught us how to do that. So they just took half of an eternal black hole Penrose diagram. So this is the initial slice that we are considering. This is the eternal black hole Penrose diagram. And we can get time evolution by evolving the endpoints on both sides forwards. You can see that the maximal volume slices are roughly double of this. And the advantage of this is that this geometry is simple. There are no collapsing matter fields. And that we also understand precisely what the state represents in the boundary field theory is that at initial times it's a thermal field double state, and then it's evolved forward in time on both boundaries. And here, this dephasing of time evolution is particularly clear. Okay, so we could consider this setup, but this is not simple enough for us. We will exploit the fact that as we lower the number of space-time dimensions in gravity, the theory simplifies. And so we will actually go to the lowest possible number of dimensions, namely 2 dimensions, in which there are still black holes. And so we will consider 2-dimensional dilaton gravity theory, the so-called JT or Jekyll-Teitelbaum gravity, to investigate this question. And this theory can be considered just as a toy model or an effective theory of near-extreme or black holes. In the interest of time, I won't say too much more about this, except that the action of JT gravity naturally contains a term which is the extreme or black hole entropy S0 times the Euler characteristic of this 2-dimensional manifold that the theory lives on, space-time manifold. And so this part is topological, and the dynamics is coming from the next term, which is a dilaton multiplying the Ricci scalar plus 2. This plus 2 is a negative cosmological constant. And there are also some boundary terms that I won't write down. And this is a simple enough theory that Saad, Schenker, and Stanford bravely went ahead and said, okay, let's evaluate the path integral for this theory. So how does that go? A major simplification is provided by the observation that phi only appears in this action as a Lagrange multiplier. And so if we integrate it out, it imposes a functional delta function constraint that on every point of the space-time manifold, the Ricci scalar is equal to -2. So we are studying hyperbolic Riemann surfaces. Okay, so we performed the dilaton path integral, and then we have to integrate over all metrics. We already have locally hyperbolic metrics, but the hyperbolic manifolds still have some degrees of freedom. Namely, we have to sum over genus, that's the unique topological invariant in 2 dimension. And higher genus hyperbolic surfaces have some moduli. Those are finite dimensional integrals. Finally, in ADS-CFT, we know that we have to consider manifolds with a boundary. And so in this picture, we are taking the hyperbolic disk, and we are drawing the boundary. This is where the dual quantum system is imagined to live. If we are trying to calculate the partition function, then the renormalized length of this boundary is supposed to be beta, the inverse temperature. And so we have degrees of the boundary graviton degrees of freedom, these wiggles, how we cut out some finite length boundary from this hyperbolic disk. Okay, so the integral over all geometries reduces to a sum over genus, integral over moduli space. In the case of the disk, there is no moduli space, it's just a point, and then path integral over these wiggles that I showed you on the picture, and they are weighted by some action. This is the Schwarzian action for those of you who followed these developments. And so writing things down explicitly, we get genus 0 wiggle path integral, that I will call it a disk partition function. And a higher genus, we can do the following trick. So here's a higher genus Riemann surface with this wiggly boundary. We can cut this Riemann surface up at the closest geodesic, at the geodesic closest to this wiggly boundary. And this is drawn here by blue. Its length is some number b. And then we have to consider this object that in the literature is called the trumpet, and remaining Riemann surface of genus G with one border of length b. Okay, and then finally we have to glue them back together. So we have this gadget trumpet partition function that depends on beta, the length of the wiggly boundary, the length of the geodesic boundary b. The moduli space integral here turns into the volume of the moduli space of genus G bordered Riemann surfaces. And finally, we glue them back together with an integral BdB. That's just the measure of this integral, and it comes out of a computation. Okay. Let me be so these things are known and are simple functions. But the more challenging thing is to try to compute these volumes of moduli spaces. And this is an important problem in mathematics. And Mirzakhani-Sfield's medal work was to derive a recursion relation for these moduli space volumes. And this later got reinterpreted by Ehnard and Orantin in terms of matrix models, in terms of loop equations in matrix models in particular. And finally, Schenker-Stanford assembled all these pieces into the following statement. They claim that the partition function of this simple two-dimensional gravity theory is equal to all orders in the genus expansion with a computation in a matrix model. So we integrate over Hermitian matrices. Some matrix potential provides the measure, and we compute the expectation value of trace e to the minus beta h. If you recall your StatMax studies, trace e to the minus beta h is the partition function. If we interpret h as the Hamiltonian, and so we are told that here we are studying an ensemble of Hamiltonians with this measure. Okay, so this is a review of their work, and so now I can come to our work, which was to ask, okay, can we actually find a matrix model representation of the volume of interior? So we use the same matrix model of Schenker-Stanford, but we want to find the object that would compute for us the volume. So for them, it was trace e to the minus beta h. What is it going to be for us? Is there any question? Okay, if not, let me walk you through some of the steps. So first of all, this model is treated in Euclidean signature. So we will have to, and whereas the volume growth was in Lorentzian, we have to go to Euclidean first. That's very easy. We know, so we simply Wick-rotate this eternal black hole at this time slice. And so, okay, we know how the Euclidean path integral that prepares the thermal field double. It's basically the Hartle-Hawking wave function in ADS. And so what we do is we have to consider this cutoff surface. We compute the geodesic length stretching between this wiggly cutoff surface, and then we continue that to Euclidean, and we will compute geodesic length stretching between these 2 points on this wiggly boundary. We will do this computation for a boundary of length, wiggly boundary of length beta over 2. And once we have the result, we will analytically continue from beta over 2 to beta over 2 plus IT. And this is the way we will get the Minkowski result. So let's see if by doing all these simplifications and going to Euclidean, whether we lost the starting point or no, and we have not. So if we do a classical computation, it turns out that the geodesic length takes the following form. It's a log cosh of pi t over beta. If we go to the regime where t is a lot larger than beta, we get 2 pi over beta t. So the volume grows indeed linearly. In a remarkable paper, Zhenbin Yang has computed all loop perturbative quantum gravitational corrections to this answer in this simple model. The way he did it is as follows. So he evaluated the JT path integral in this geometry. So there's this blue boundary, it's a geodesic boundary of length L, and there's a wiggly boundary of length beta over 2. And we just have to evaluate this. It's a simple Bessel function in the end. And the interpretation of this quantity is that this is the Hartle-Hawking wave function in the basis where the geodesic length operator is diagonal. So just think of quantum mechanics. We can compute simple one-particle quantum mechanics. We can consider the position basis or the momentum basis. Just like that, in this model, you can consider the wave functions of this universe in the geodesic length basis L. Okay, so once we have this wave function, then computing the volume is really easy.
Sorry, excuse me, can I ask a question?
Yeah.
So I think you want to compute this maximum time slice volume.
Yes.
So how this calculation pick up this maximum value?
Great. So the maximal volume is like the saddle point. So I will describe to you a quantum mechanical expectation value. And if you go to the regime of the classical regime, which is the hot black hole regime, then this computation will be evaluated with saddle point. There will be a most likely this wave function will be very peaked at the maximal geodesic length, and this is how it emerges. But here I'm describing quantum corrections to this, and the appropriate quantum generalization is not to take a maximum, but to take an operator and evaluate its expectation value. Does that answer your question?
Okay, so are you claiming this? So this classical contribution plus quantum correction gives a full answer to complexity?
Well, that's the
holographic complexity.
I mean, that's the only thing I can imagine in the quantum regime. That's the only generalization that I can imagine to be a quantum generalization, because as you said, there in the quantum regime there does not exist a well-defined geodesic length. The wave function is spread out in this basis. So the only thing I could think about, but also so the only thing I can imagine is to compute the expectation value of this operator, but maybe somebody else can come up with some other prescription.
I see. So this prescription also maximizes Hartle-Foking wave function in some sense.
So it's computing. Let me write down the answer. So what we are doing is first we are considering the probability density of having geodesic length L. So that's obtained by taking the absolute value squared of the wave function. Then we multiply it with L, and then we integrate over all L's. And it turns out that the measure, again, this can be computed. In this case, is e to the L dl. And if you evaluate this integral at large times, it can be evaluated with saddle point. We again get linear growth, but with a quantum corrected coefficient, which at high temperature reduces to 2 pi over beta.
Thank you very much.
Okay, great. So
Excuse
even
me,
though
I also have a question, Mark.
Okay, let me just say one thing. Even though this is an all loop calculation, and what by all loop I mean that if you expand in the amplitude of these wiggles and then but go to all orders in this expansion, this is the answer that you will get. And in a higher dimensional gravity theory, you cannot dream about doing this, but here it was done. And even though it was done, we didn't get any significant change in that graph. It's just the slope got renormalized, but it's still linear growth forever. Okay, go ahead.
Excuse me. So when you write the Hartle,
Yeah,
that's wave function. So is it just a path integral with some fixed boundary condition?
Yeah. So the boundary the only boundary condition in this simple theory is the only thing that you can fix is the length of the boundary, and so you fix a geodesic length L, and the weakly, and here this other boundary is not a geodesic; it can fluctuate, and you fix its length, and you ran out of all your degrees of freedom, and so then then you have to do the path integral for all these configurations. I mean, many wiggles are possible. The only thing that is fixed is the length of this boundary.
So is it calculated in JT gravity?
It is calculated in
okay.
JT.
And then so you also take into account the full correction. So you say that it's all order result, right?
Yes. Yes.
I see. Okay. Thank you.
Okay. So it was an all-ordered result in perturbation theory, but we know that there are non-perturbative effects in this theory coming from topology change or higher genus surfaces. So I won't have time to describe this in detail, but hopefully this picture will be enough. So at genus 0, what we did is basically cut open this disk and then insert in between this quantity L and then compute. So the higher genus generalization of this, just like as in the case of the partition function. So let me remind you what we did there. Basically, topologically, we cut open a hole here and then glued in some complicated topology. And this is exactly what we do here. We cut a hole both on the bra and the cat, and then glue in some complicated topology. This complicated topology can either be disconnected for these two guys or can be connected. And then in between, we put in this L and then integrate just like here. Okay, if we go through that calculation, we will find what we are looking for, namely a matrix model representation of this volume. So let me write down the answer. It will involve some new ingredients. I'll hope to motivate it a little bit. So it's a double integral over the energies in this matrix model. So those are basically the energy eigenvalues of this matrix. And we have the density, oops, okay, sorry, I skipped too many things. So let me first define the spectral density in matrix models. So the partition function, as in elementary stat math, can be written as follows. Integral over energies, the density of states times the Boltzmann factor. So if you have just a normal quantum system, then this density of states is just the sum of delta functions. In matrix models, this density of states is an operator whose expectation value we can consider. So in terms of this, the result of this computation is that the volume of the black hole interior is as follows. It involves a density 2-point function of the matrix model with center of mass energy E and energy difference omega. There's a very important 1 over omega squared factor, an unimportant density of states of the matrix model, unimportant Boltzmann factor, and the time dependence comes from 1 minus cosine omega t. So here we see again what we talked about in the intro, that the energy differences are conjugate to time. So we have this product omega t, and we have to evaluate this double integral. So okay. So this is the answer of this is the end result of a computation that I didn't have time to discuss in much detail. But basically the point is that this gluing in of complicated topologies is very similar to what we would have if we computed a 2-boundary partition function. It's the same kind of sum over topologies that appear. And so if this density 2-point function is obviously related to that object because it's just a double Laplace transform of that. And this same quantity appears in the computation of the volume. So finally, in matrix models, this density correlator is very well understood. It's completely universal, independent of the matrix potential. It looks as follows. It starts from 0, then it has this wiggly nature, and finally it goes to a constant. This constant is a disconnected 2-point function. So it's just 1-point function squared. And these wiggles represent the fact that the spectrum of a random matrix is rather rigid. So the eigenvalues are roughly equally spaced, and their separation is the mean level spacing 1 over rho. Finally, this 0 is expressing the well-known fact that eigenvalues repel, and there's 0 probability to observe 2 eigenvalues sitting on top of each other. So what we are exploiting here is the very advanced understanding of density-density correlators in matrix models. That's why we are using the matrix model description instead of the direct gravity computation. So if we plug in this density-density correlator into our final formula, then we get the following. So from this disconnected contribution, which was just this constant here, we recover the genus 0 answer, the forever growing contribution. And from these wiggles, at early times, we get basically nothing. It's suppressed by e to the 2s naught. But at times of e to the s naught, at the Heisenberg time, the contribution from these wiggles to this integral starts to grow, and it grows with a negative coefficient linearly. And magically, the slope of this guy is equal to the slope of the blue guy. And so they end up canceling perfectly. And so from the sum of the two, we get this orange curve. And this orange curve is exactly how complexity was imagined to behave in chaotic systems. So in summary, we consider the interplay between gravity and QFT. In gravity, there's a ubiquitous phenomenon that the black hole interior grows. This was related to complexity growth in QFT. But we noticed that complexity stops growing at the Heisenberg time, and then we asked, is there some new effect in gravity that stops the growth? And we found these new effects. These were new non-perturbative effects associated to topology change, and they indeed stopped the growth of the appropriately defined quantum generalization of the volume. So I hope we have learned something new about both black holes and quantum field theory from this work. Thank you very much for your attention.
Thank you. We are open for questions, comments.
So this Einstein-Rosen bridge is growing linearly in time, but the size is shrinking. But when this new non-perturbative effect is showing up, the size becomes like some specific scale, or?
So the size, you mean the width of the Einstein?
I'm thinking of higher dimensions than,
Yes.
then size shrinks and then lengths get longer linear in time. But
yeah, but the size shrinking is not very significant, at least in this regime of near extreme or black holes. So this JT gravity can be obtained for near extreme black holes from an S-wave reduction the black hole is a sphere, and you do an S-wave reduction on this, and this is how you get this JT gravity. And so the size of this transverse sphere or transverse complicated topology doesn't change much as you go through. It changes a little, I completely agree with you, but it's not significant. So the volume will roughly be the length through it, at least in the near extreme or limit. I haven't analyzed the Schwarzschild case. So
what is this non-perturbative effect in gravity?
What is it doing? So it's changing it's a Euclidean geometry. So in Lorentzian, it's hard. It's really an instanton. So what it's doing, there are words that you can say that somehow this spatial slice emits a baby universe in Lorentzian, and somehow the tendency to grow transfers to the growth of the baby universe, but you're not capturing it, the growth of that with the volume, and that's why the volume stops growing. But here I really just did a Euclidean computation, and I wasn't bothering too much with this baby universe emission, which is supposedly a Lorentzian picture, but there are many subtleties associated with large diffeomorphism symmetry. So I would refrain from attributing too much importance to this picture.
Excuse me, may I ask a question?
Yes, please.
Of course.
So for spectrum form factor, we can
Yes.
use a large N saddle point evaluation for random matrix theory, or even for SYK, we can do that. And then the linear in time growth in spectrum form factor is basically captured by the large N wormhole type of saddle point approximation, right?
Yes.
So can
in JT language, you're talking about the double trumpet, right?
Yes, yes.
Okay. Okay. Just
so can you give the same interpretation for your computation?
Yeah, that's an excellent question, and the answer is no. So here, the linear growth. So in the spectral form factor, the linear growth came from this instanton that you're talking about. Is a genus 1 surface. It's called the double trumpet. Here, the linear growth was classical. It came from genus 0, just the disk. So it was more easily visible. But then this saturation to a plateau, that cannot be associated to any particular instanton. It's coming from the resummation of all instantons. So just like in the spectral form factor, the plateau is not understandable in terms of just one particular instanton or one higher genus surface. Here again, the plateau cannot be understood just from one of those, but the linear growth can be understood even classically. So it's different.
I see. So in your computation, this just zero genus wormhole type of saddle doesn't play any crucial role?
No. In fact, for experts, so this is the spectral 2-point function, and this is actually the same input that goes into the computation of spectral form factor, but it goes into it in a rather different way. So there's this disconnected contribution. It doesn't give anything for spectral form factor. For us, it gives linear growth. And then the genus 1 contribution would be just basically 1/2, where you average this sign squared out to be like 1/2 because it's oscillating like crazy. 1/2 over pi squared omega squared. So that's the double trumpet contribution. And for us, if we just plug that into our formula, we would get divergence. So any individual guy actually gives a divergence, and that divergence is only regulated by this eigenvalue repulsion, which in the JT language is only visible by resumming all topologies. Does that answer your question?
Yes, thank you very much.
Thank you.
So what's the role of Boltzmann time here? Because in boundary, Boltzmann time, I don't know well enough about Boltzmann time, but boundary theory is compact, so you repeat some sense, right? But here,
yes, okay. So, yeah, Poincare time is even later. It's doubly exponential, okay. And I don't know of anybody who has a good understanding of physics at that time scale. But you are right that if we have any quantity, it should eventually experience recurrence. But what we are computing is not sensitive to it. And I think nobody knows how to get those things in matrix models, for example, how to go to those timescales and capture this recurrence physics. So very good question.
Thank you.
Can I ask a question?
Yes.
Do you think your analysis also something related to black hole singularity? Especially if we consider higher dimensional case, in the end, later time, it gets closer to singularity. Maximum time. Or do you think
maximal volume slices somehow tend to avoid the black hole singularity. So as you can see here, these guys are rather repelled by the black hole singularity. And we were doing Euclidean computation where the black hole singularity is not visible. So I don't know. I would think that we are sensitive to anything that goes. Okay, how would I say it? Yeah, the best answer is I don't know. There are speculations in this field now that maybe these these. So we were considering ensembles, and that the black hole singularity is somehow encoded in the noise on these quantities. But in people mention half wormholes and stuff like that. So I'm not sure if our quantity is sensitive enough to know about the black hole singularity, and I haven't seen any sign of it in my Euclidean computation.
I see, I see. Also, the reason you have this saturation of this length, can we have some intuitive understanding in terms of your non-perturbative correction related to the previous question? But somehow this length is somehow growth of length is stopped because some bubbling like structure in the space-time?
No, so since it's coming from a resummation effect over different genus space-times, it's very hard to understand it directly from space-time. I mean, if you're thinking perhaps about these FZZT brain-like things in JT Gravity, then perhaps you can understand it from that extension of JT Gravity, but we didn't really explore this.
So you're saying very, very quantum. So there are no way to understand this classical way.
Yes, yes.
No single geometry.
So for us, the practical things seem to be just to, whenever it was possible, to make that step and go to the matrix model and work there, because that's the simplest description of the physics. But I agree that way we are losing the nice space-time interpretation of what this volume is.
I see. So I have a final question about also your calculation, but can we see some kind of Poincare recurrence? It's probably exponential of exponential s.
Yes,
yeah, of course it's much longer, so it's not trivial, but I'm just so curious about it.
I don't know how to see it. I think it's an open. I think it might be the next frontier to try to probe physics at that time scale, but we are not there yet, I think.
But in principle, probably you can find it. Is that true? Or random matrix approximation somehow?
I mean, for each individual random matrix, the exact time of Poincare recurrence will be at different times. So you somehow, I mean, you must see some smeared out effect of it, but I don't know of any work, but maybe that's just my lack of knowledge, where they saw any, or where they identified any sign of Poincare recurrences. So I don't know how to see it from matrix model.
I see. Thank you very much. Yeah. Also, thank you very much. Very interesting talk.
Thank you.
Any other comments? Questions?
Yeah. So even though it's a little different, can you derive this linear growth from fusible picture?
From fuzzball picture.
Yeah. It's another alternative of understanding black holes. So
yeah,
it should be there somewhere.
I mean, fuzzballs are Lorentzian solutions. Right. So it's a good question if somehow the maximal volume slice can get like very complicated in the fuzzball. That's a good question. That's a good challenge to the fuzzball people to see even the linear growth, not just not the saturation, but the linear growth. Whether there is linear growth in their story or not. I mean, if the linear growth here is coming from the interior, they don't have an interior, but they claim that oftentimes like that fuzzballs can reproduce many aspects of like there's this idea of fuzzball complementarity, that if you probe fuzzballs with long wavelength of observables, then they behave just like black holes. It would be interesting to see if for this probe they behave like black holes or not. It's a good question.
Okay, it was very nice talk and very interesting set of discussions. If there is, unless there is there some other question from auditorium? No? Okay. If there is no further question, let's thank Mark again.
Thank you very much for the invitation and the nice discussion.